It's always nice when a customer's easy to hold of because it means I can get started on work quicker than I normally would. First things first, we need to make sure that we get all of this excess voltage internally gone so I don't end up shocked myself. Got my little pokey stick here. You can actually see the voltage there. If we just make contact there, just to make sure they're all drained. Last thing I want is to poke my hand around inside of there and feel that unfortunate, really unpleasant zap that comes from caps discharging. Felt that on more than one occasion. Everyone who works on amps will feel it at some point. Despite our best efforts, you're always just going to make that one little silly mistake. But thankfully, we've got most of the other safety things in mind to prevent that from actually happening. So rather than copping a full, 240 volt or, high voltage directly through you and taking you out permanently, it's just a bit of a love bite. So I got the go-ahead from the customer, and what we're going to be doing is all the good old-fashioned upgrades to make this a lot more longer lasting and harder rocking and all that stuff. So bye-bye caps, bye-bye 100 ohm screen grid resistors, C to those tubes. Put those in. Since we're going to be inside as well, we may as well replace that jack. It's not going to cost the customer any extra really because I'm already inside doing all the work. Replace that cruddy sort of box jack type thing with a good quality metal Switchcraft shorting jack. And it's going to last for years and years and years to come. The customer said he'd much prefer to spend a few extra dollars to get something that's going to be a reliable, robust workhorse. Do it once, don't have to think about it again. So the next task on the list is to get the board out and start removing components. Let's get started. With the knobs removed, I'm going to put all of those in a Ziploc bag. One of the things we want to make sure as well is I've seen more than one of these amps come in that's missing these little doovers here. So they help to prevent the knob from sort of smashing the shaft through the back of the pot there or damaging it. I mean, probably would have just been better to actually use a proper, pot that had a bushing on there and washer and the likes, but what can you do? At least they tried. But when these go missing and you put the knob on there and you go out and they knock there, they can really take those pots out. And that's an expensive repair because you've got to gut the board and do all that. So just keeping them nice and secure inside of a baggie is going to make for a far easier process. And since we're already here as well, we may as well give everything a nice little old-fashioned dusting and cleaning because I want to hand it back to the customer in a good state, not only, electrically and the likes, but make it look like, we went that little extra mile because it's about having pride in your work, wanting to not just hand something back that may not, it takes a couple of seconds for me to do this. But I know if I keep on top of things like this, then I'm going to at least make sure the customer gets something that is worth every penny that they've paid. My services aren't cheap, so I have to justify them in every way that I can. This only takes an extra couple of seconds. Doesn't go on the bill, it's not billable, this part here. And it just makes for a nice, shiny cover there. So it's going to have a whole bunch of new components inside. It's going to have a nice new look on the outside to match it. So the total plan is I'm going to pull out these blue IC caps, replace them with some nicer F&Ts. Going to be higher temperature coefficient rated, so they're going to be 105C. We're going to pull out the 100 ohm screen grid resistors on here that are way too tiny of a value and underrated. I'm going to throw in some 1K ones because that's going to minimize sort of chewing out what's there. We're also going to change out the bias resistor to increase the negative bias, therefore running the tubes at a far more reasonable plate dissipation. Should help minimize the chances of arcing and flashover inside. It'll help minimize them being worn through and just burnt up really quickly, and just make for a far more reliable amp. Oh, and we'll also replace this plastic jack here with good quality switchgraft switching type one. So at least that way it's going to just last and last and last and last. So let's start getting these components out and go away from there. So with a couple of components already swapped out, one of the next things we need to do is, because this uses lead-free solder and I'm working with leaded solder, we've got to remove traces of all the old stuff, because if you don't, it ends up going crystalline, causing issues. So we get some good old-fashioned solder wick just to remove as much as we can from the pads, because the less there is there, the less likely we're going to have any sort of issues going forward. Lead-free solder is really good for the environment, because that way you got less sort of stuff leaching into water supplies, into the soil and into people's bloods, but it is a lot harder to work with and more prone to problems, because we're only using a little bit here and it's just little old me doing this kind of stuff. It's easier to just use leaded stuff. Cool. We've removed all that. Now we can connect up those little cables, because we're going to run little sort of fly leads here to connect the switchgraft jack up onto the chassis. Now before we go and install the new caps, what we want to do is we want to get rid of the old elastic silicone that was underneath the caps there, so we can put some fresh stuff down and adhere them to the board, make them nice and solid. A couple of ways you can go about doing this. Of course, you can use a chisel if you know how to use one of those, or in my case I like to use a razor blade because it's a little bit easier. Don't have to, grab anything too crazy. You just slide it under like that and it just slices through like a hot knife through butter. So the next step is going to be get those caps in, put some elastic underneath. What we've gone for is a set of F&T 500 volt rated jobbies. So higher voltage rating than the previous ones, are much higher quality as well. So these are just going to last and last and last. They are 85 degree rated. Unfortunately, I don't have any 105 degree rated ones in stock, but still they're going to be much, much more reliable than the old ones. F&T do really, really good stuff. With a bit of Celastic on there now. Celastic, of course, is it's trademark name for a type of neutral cure silicon used for electronics. This is specifically an electronics silicon. It is designed for that. It's not the stuff you use in your bathroom. It's nothing like that. So it's designed to not cause corrosion on the metals and the copper and all the rest of that around. And it's going to hold the components in place. These are big chunky caps, and because Fender still insist on using the axial caps instead of moving over to radials for stuff, they're going to flop around in the breeze, and on these PCBs there's little tiny pads that sort of hold things in place. It's not like the old dog boxes underneath the old Fender Twins and all that the caps are also held in place by a bit of foam. Yeah, the foam disintegrated over the years, but at least it had some more mechanical connection there. So we're going to put these in, going to solder them up, and then we're going to do all the fun testy bits and all that kind of stuff. One thing I always like to do as well when I'm installing caps, I like to make sure that I've got the pertinent values pointing upwards. So the next person who's rummaging around inside, if this amp doesn't come back to us, is going to at least know what values that were put there. More than once I've gone in to repair an amp, someone else has already been in there, and the component designators are underneath there, so I don't know what they put in. More than once I've pulled them out and found they've put the wrong value in. So these caps were a bit of a tight squeeze. They just fit in the footprint of the old ones were there because they're ever so slightly longer. But with that Celastic underneath, that's going to hold them in place as well, give them that good solid mechanical connection, so they're not going to be going anywhere, which is a big plus, and they're firmly against the board, ready to rock and roll. So far, we've managed to get the caps all replaced. We've put in some new 1K 5 watt screen grid resistors up here. Floated them above the board as well to give them a little bit of thermal distance between the PCB and there, just in case they pull some extra current and whatnot. It just makes a lot more sense rather than having them plucked right against the board. So we got that all sorted. We've got that all sorted. Got the fly leads there ready to install the jack once that's all good to go. So it's time to start putting things together. Actually, no, wait, I lie. Getting ahead of myself here, just looked at my list. Still got to replace the resistor there. So there's a 33K resistor, which is R51, yep, 333, yep, 33 with 3 zeros afterwards. We want to swap that out for a 24K, and that'll drop it down to a bit of a nicer value for bias purposes and lower the plate dissipation and the idle current on the output tubes. Give them a bit more life. I'm going to do that now. Now that we've swapped out those components, got a little bit of ugly flux here on the board, so like there and whatnot. Some techs might just leave that behind, but that's generally not what we try and do here. I want to get rid of that just because the less that there's on the board, obviously it looks nicer the next time someone's in there, but also it's just, you know, it's less likely to end up as corrosive, having issues, and it's just good housekeeping. Means I could also have a bit of an up-close view of things that we've removed and repaired and all the rest of that to make sure there's no dry solder joints or anything floating around, because I want to be able to hand this back to the customer as what we promised, which is a more reliable, more solid amp. So a little bit of flux cleaner here. Some people use isopropyl. I like this dedicated flux cleaner. I tend to find it goes through a bit faster, but more importantly, it smells like orange. It's like orange oil or something. It's phenomenal. And it just makes light work of that flux buildup. That one's not even my flux. That's flux from factory. Because there are a couple of parts on here that would have been soldered on by hand at factory. So those are cable connectors for the reverb connection and that. So the board looks a lot better now that I've given it a bit of a clean. So I've gone through, removed all the flux residue that's on there, given it a bit of a rinse with isopropyl alcohol as well, just to make sure that any guck that might be on there is all removed. And yeah, give a bit of a check to any of the solder joints there, make sure they're all good and they're all looking pretty hunky-dory. So the next step is to put this back inside its case, reconnect things, and start doing tests. We've installed the new jack up here, so that's a good quality Switchcraft 11 style. Is 11? 12. 12A. Switchcraft 12A jack, so that's the shorting type. That'll pretty much outlast, you know, most components in the amp, all going well. Left enough lead on those cables, on the leads as well, so that if someone needs to change them out in future, they're easy enough to change. New caps, rock and roll, they're gonna last quite some time. Then hiding under here are some heftier, chunkier 1K 5 watt screen grid resistors. That's going to help to minimize any issues with screen currents. Like I said earlier in the video, it's not 1964. Tubes are built a little differently these days. So the next thing we're going to do is we're going to just double check the bias, make sure everything's all as it should be. Now in order to make sure that we've cooled down that bias enough, what I'm going to do is I'm going to use the resistance method across the transformer. Each side of the transformer is going to have its own resistance, so we can measure that up, and then we turn the amp on, power it up. Once we know the value of those resistances on either side of the transformer from the center tap, calculate what the voltage drop across it is, and then use that to figure out exactly how much current is going through each of those tubes. That's a far better way of doing it than, say, for example, soldering in a 1 ohm resistor on the cathode and having to do some extra things, obviously modifying the amp, or trying to desolder and shunt a wire through there. This way is pretty darn accurate all in all because, well, you know, Ohm's laws, all that. If we know 2 of the given values, we can figure out the third one pretty easy. So looking on the right transformer, it's hanging at 94 ohms. And then the left one, we connect that there. It's giving us a reading of, once it settles down, 95.6. So left, 95.6. So even though left and right side of the transformer have different DC resistance to it, the main thing when it comes to how matched either side of the transformer is has to do with impedance and the ratio of the turns there. So both of those connections from the center tap have the same number of turns around the transformer. That's all the AC signal cares about. So that part's easy. But knowing those DC resistances, we can calculate what the bias is at idle. So we're going to start with the right-hand side, over here, like so. Run it over to voltage, and then we're going to connect it up to power, turn it on, and get ourselves some idle current happening. I'm going to power it up slowly first and just make sure everything's all good. So now I want to take a check of the nodes across there and make sure everything's all hunky-dory. So here on the first node, we've got 339, which is a pretty nice looking number. That one there. Next node, 321. Which is good. 280. Go down to number 3. 255. Awesome. Awesome, awesome, awesome. So the next thing we want to do is we want to calculate what the voltage drop is across either side of those transformers, and that'll tell us what the idle current is on that. So in order to do so, we need to actually measure across those two transformer halves. So if we go from ground there over to that side, that's now the node where that is. So on right-hand tube, we have 1.944 volts. 1.944. And on the right-hand side, stay, 1.93, no, 1.94, yeah, 1.94, 940. Yep, so that's sunk down a bit there. Just double check the other side quickly again. Stay. 1.94, no. Yep, 1.944, awesome. So what we'll do is we'll do a little bit of quick math here, just to figure out what the idle current is. So a little bit of mathematics there, we worked out that the right tube is pulling 20.68 milliamps and the left one is pulling 20.29. That's pretty darn close, all things considered. You know, that's like half a milliamp out. Just pretty good all in all. So the next thing we want to do is we want to measure what the actual voltage is on the plates of those tubes. And then once we've got plate voltage and we've got the current, then we can work out what the power dissipation is across those tubes. The right one is currently pulling 336.7 volts. Currently has 336.7 volts across it. And the left-hand one, wow. Try that again. I think my parrot clips are starting to get a bit worn out. Stay. And left tube is pulling, the left tube is currently at 336.7 as well. What we've managed to do is tame that considerably from originally pushing tubes to stupid levels to now running them closer to 57.5% dissipation across both of them. Yeah. The numbers don't have to be accurate down to super tiny percentages, but that's a lot better than pushing them at, say, 90 to 100%. These tubes are going to last a lot longer. And they're going to sound, for some people a little bit nicer, some people like them a bit cooler. So we've got a well-balanced set of tubes, we've got some good quality upgrades there, stuff that's going to now last. The next thing we need to do is just plug it in, give it a quick test, make sure it sounds the way it should, there's no extraneous hum or noise, then close it back up and send it off to the customer and hope that it lasts for as long as he needs it to last. So we've got this all plugged in, powered up now, ready to rock and roll. Wow. Yeah, it seems to be working, doing the thing. Cool. Is reverb still doing its thing? reverb works, that works. EQ, treble. Fat switch. Yep. Oh, that's shiny. Very, very bright sounding. Yeah, I'm no bluesman. I don't profess to be, but, you know, amp does what it needs to do, all that kind of good stuff, which is excellent. Yep, sounds like a Blues Junior. Nice. Let's say we bolt this back up, send it on off to the customer. No one really needs to hear what this sounds like now because we didn't do any mods, we didn't do anything, you know, to fix it and all that kind of stuff. And everyone knows what a Blues Junior sounds like. Don't need any of my terrible playing on this one here. But if you happen to be in Australia and you do want your amp to be more reliable, we've now started offering a couple of fixed price upgrade kits. So we'll go through and sort of overhaul the amp, make it, we'll fix the problems that we know will happen. There are certain things that are going to happen with certain amps, with certain brands that you just can't avoid. It's in the design. We'll fix those, make them preemptively good to go, and then that way you've got an instrument and an amp and a tool that's going to last the long haul. Until then, make sure you like, subscribe, hit the notification button, and of course you can visit us online at drgear.com.au for any of your instrument and component needs. So until next time, we'll see you then.